So Sheila, if you'd like to kick us off, please. Thank you.
Thank you very much, Chloe. Welcome, everyone. Welcome to the TWI Innovation Network webinar to celebrate Corrosion Awareness Day, which is on the 24th of April. We are going to look at corrosion science and engineering, talk a little bit about materials and coatings research by the Materials Innovation Center. So Materials Innovation Center is a collaboration between University of Leicester and TWI. And I'm the director of that center. I've been director since 2018. Today we have got a few presentations this morning. Let me go to the agenda this morning. So to kick us off, Irmak Kokan, who is the Innovation Consultancy Manager at TWI, is going to talk a little bit about how you can collaborate with the Innovation Network and be part of the network, and how you can work with the innovation centers and how we can work together to develop technologies that'll help us in the future. And then I'm going to talk a little bit about MatIC, or the Materials Innovation Center, and to set the scene for the technical talks from MatIC. So that will be Kranti, who is a research fellow in MatIC, who is going to talk a little bit about the Marie Fellow project that he was doing on zinc electroplating or electrodeposition. Then we have got two talks talking about corrosion mitigation in offshore environments. First one by Adamantini, who is a postdoctoral research associate in MatIC, who's going to talk about coatings for offshore applications, primarily duplex type coatings. And then we have Adriana, who is going to talk about thermal spray aluminum and how flow can affect the corrosion behavior of these systems. And last not the least, we have Naomi Ott from who is currently the chair of Young EFC, so Young European Federation of Corrosion, and she'll talk a little bit about how to create a network for people who want to come into the corrosion community. And then we'll have Q&A at the end of the technical talks. So for those who have questions for the talks, you can send the questions via the Q&A that you've got in the control panel part of Zoom, and we'll address them as and when we get to those questions. And if there are questions that have not been answered by the end of all of the talks, then the respective speaker would address those questions. So without further delay, I'll pass the mic to Irmak, who is going to talk about the power of collaboration. Irmak, over to you, please.
Thank you very much. Let me quickly share my screen. Welcome everyone. So I'll be talking a bit about our TWI Innovation Network and how we manage collaboration through that. Apologies. So our TWI Innovation Network, which is TWIN for short, has been created to provide our members with an access channel to public funding opportunities through collaborative projects, so that we can facilitate a network of driving members to work together and provide the process of knowledge transfer between academia, ITRs, and private sector. So when we talk about TWI Innovation Network, we do have very different components. So we can have private technology innovation partnerships with industrial companies, and we do have several PhD programs such as National Structural Integrity Research Center, but mainly what we want to focus on today is the innovation centers, virtual innovation centers, and technology acceleration programs, which are TAPs. So with regards to innovation centers, as Sheila mentioned, MatIC, Materials Innovation Center, being one of them that we established with Leicester. We do have other innovation centers such as Manchester Metropolitan University, Lancaster, Teesside, University of Arts London, Brunel, University of Essex, Anglia Ruskin University. So we do have many different innovation centers created with different universities. As I mentioned, technology acceleration programs are for SMEs to, again, assist them with regards to their collaborative research activities. Also, as TWI, we do have our own technology groups where we develop several different technologies. And as a company, we work very closely. Of course, we are a membership-based company, so we have a large amount of industrial members that we work very closely so that we provide this network of collaboration opportunities within TWI Innovation Network. How do we help these members of TWI Innovation Network, TWIN? So we, as the Technology Innovation Management team, assist you through the public funding proposal development process by providing expert advice on research funding programs, helping shaping your research concepts, finding the right partners within the work and beyond, and also writing and submitting your research funding application. So the main focus that we have with regards to collaborations here, especially finding the right partners. So as we say, we do have a very large network within our TWIN members, but because TWI is a global company, we do have quite a reach globally as well. So if we are building a proposal, we don't necessarily have to find the members within this TWIN network, which is very useful, but we can reach out globally as well. So as an example of this, I wanted to highlight some collaboration activities that we have taken on. Obviously, we do have focus on IUK Innovate UK projects or Horizon bits, but we do have a reach for, like I said, global challenges too. An example being Abu Dhabi Singapore Smart Cities Open Innovation Challenge. So we brought together a virtual innovation center that we have with Teesside University and our Global Technology Center that is situated in Singapore so that we can work on this challenge and provide a solution for the challenge. Other examples, like I said, bringing together innovation centers, SMEs, innovation centers, and industry members, and also different innovation centers together so that we can build this platform of network either within TWIN or externally as well. Like I said, how we can support our members, we can start from the idea generation, turning those ideas and initiatives into concepts, then trying to build the proposal with you with regards to formatting the consortium, managing the consortium, writing the proposal, managing the financial and other administrative details of proposal, writing and preparation. Through the end, obviously assist you with regards to proposal review activities, and at the end, checking all the forms, again, administrative actions, and to the point of submitting the proposal. So it's the whole life cycle of developing a proposal for a public funding program. We also do offer different innovation consultancy services to the organizations we work with. Other than research proposal development activities, we do work on innovation and technology management. These do link a lot with the proposal development activity, obviously, which would be the end initiative of a long strategy that has been developed. So that means we could assist you with regards to building an innovation management system, innovation audits, idea generation workshops, how to manage intellectual property within innovation space, or creating technology roadmaps, strategic intelligence, technology insight, different activities, so we can assist you through those processes as well. You can reach out to us either from our email info@twinnovationnetwork.com, or we do have a platform, TWI Orbit. Please feel free to review our platform. It's where we bring together our network members, where we share funding opportunities, collaboration opportunities, and you can just sign up freely. So thank you very much.
Thank you, Irmak, for that introduction to the innovation consultancy and the network. And it's great to see that you're trying to develop a network that'll help people collaborate and achieve things that won't be otherwise possible for an individual or an individual organization to do. So I'm going to now go to our technical part of the of the event, and let me go back to the agenda. I hope you can see my screen.
Yes, we can. Thanks, Sheila.
Okay. So in terms of the talk, as I said, we have got 3 technical presentations from MatIC, or Materials Innovation Center, as I said. And in terms of just a brief introduction to Materials Innovation Center, it is a center, as I said, established by TWI and in partnership with the University of Leicester. In terms of research, you can see on your right, we do quite a lot of work on advanced materials and coatings, electrochemical engineering. Corrosion is one of the key elements of that. We are looking at low carbon technologies, hydrogen renewables, geothermal, recycling technology and waste utilization. We have got a project currently looking at recycling, and then advanced manufacturing, materials modeling, and materials genomics, especially using AI for some of those activities. So we are based at TWI site, so you can see the map of the UK there, and University of Leicester is in the Midlands, and TWI headquarters is in Cambridge, and we are based in the nice countryside about 8 miles south of the city centre, Cambridge, by the lakes, and we work very closely with colleagues within TWI and the Innovation Network to deliver collaborative projects. So in terms of research within MatIC, as I mentioned, advanced materials and coatings, there are several projects we are looking at developing coatings, and one of the talks today by Kranti would be on development of coatings. So it's a combination of both electrochemical principles and advanced materials and coatings development. We have projects on geothermal. One of the last ones, the European project GeoHex. We completed it in 2023. Recycling technology and waste utilization. Currently, we are looking at multi-material system recycling. So one of the issues with recycling of polymer metal systems is that you can recycle one or the other, but both in combination becomes difficult. So we have a project we are looking at development of solvent systems to delaminate this multi-material system so that it can recycle individual components quite easily. And of course, as I mentioned, we do have an area looking at advanced manufacturing, materials modeling, and using AI-based methods to do what we call materials genomics. Here's a snapshot of some of our projects, and you can see their completed projects as well as I mentioned, GeoHex, a project that we completed looking at geothermal heat exchangers, and Solrec 2 is the one where we are looking at multi-material system. Sunray is looking at novel perovskite photovoltaics. Forge, developing novel complex materials. So these are composition complex alloys that we are developing using machine learning and then characterizing the materials that are developed later on. Innovative drinking water disinfection, H2O for all, is looking at developing technologies for safe drinking water. And Serene, which started this year, is going to look at novel energy storage system, so combination of thermal energy storage and electrical energy storage. And there are several other projects that I haven't actually talked about. So in the past 6 years or so, we have managed to get over £3.5 million worth of funding through UK government, Innovate UK, and European projects, and thanks to the Innovation Network for putting us in touch with several of the partners in Europe and also helping us develop some of these bids. So MatIC's focus is on causation rather than correlation. So I like to present this slide where you can see the person on that vehicle is actually just looking at what others are doing, not really understanding the reason for what others are doing, and just correlating rather than finding the causality. So this is something that MatIC wants to do, is to look at causality rather than be that guy at the top. So how we do that? We try to understand the link between processing, its structure or microstructure, and try to correlate that with properties and performance. And we do that through detailed characterization and try to understand the cause of certain behavior, performance-wise or property-wise, that stems from microstructure that is derived from the processing related to that particular material. So this is what fundamentally MatIC is trying to do, to understand how microstructure drives the properties and performance of materials, which inevitably is linked to the processing of those materials. So I'm going to present just one slide where you can see that this is something that we have been trying to do to understand the fundamental principles that govern properties of materials. So this work was carried by Adriana, who would give a talk today. So we were trying to understand how defects within thermally sprayed aluminium so give rise to the behavior of those, or how defects could or couldn't be protected when we have exposed defects in synthetic seawater in this case. So we used in situ imaging and electrochemical monitoring to understand how the activity when you have a defect within the coating. So in the middle, you see there is a defect. So that defect is the steel substrate, and the rest of that circular region you can see on the outside, the ring, is actually thermally sprayed aluminium. And so as you see, as time progresses, the activity of that coating system goes down. So you can see that bubbles have stopped emanating from the middle because the steel in this case is acting as a cathode. And in those areas, you'll tend to form calcareous deposits. So later on in the talk, both Adamontini and Adriana are going to explain some of the fundamentals that we have covered in this particular area of mitigating corrosion in offshore environments. So in terms of the center itself, we have two academics. I'm the director of the center. We have 5 full-time equivalent staff. So the number of staff is actually more than 5, but the equivalent full-time number is 5. 3 current PhD students and 7+ research projects at the moment. So as I said, my name is Shiliditya Paul. I'm the director. And then we have got science director, Professor Hong Dong, who is very well known in the field of melt solidification processes, and he's leading the UK CDT on digitalization of metal processing industry. 3 doctoral researchers, Nigar, Adriana, and Arunima. Adriana is going to give a talk today. Then we have got several senior researchers, Vikas, who has been with MatIC since 2019. Kranti, who was a Marie Curie Fellow, and he's also going to give a talk today. Adamontini was previously a PhD student, now a postdoctoral researcher in MatIC. Deepak is a postdoctoral researcher. Adamontini is also going to give a talk a bit later. Madhuri is a research associate, and Tianma works with Armantini on the recycling project. So as I said, these are the three researchers who are going to give MatIC talks today. So in terms of the talks, as I mentioned, Kranti is going to kick us off the technical part of the talk, talking about his project on zinc electrodeposition. So these are systems that are used to protect steel. We have all heard of galvanized steel. So he's going to talk a little bit about zinc electroplating. Then Adamantini and Adriana, they are going to cover how to protect structures in marine conditions or marine environments. So Adamantini is going to talk about duplex coatings, zinc aluminum with organic systems on top. And then Adriana is going to talk about effect of fluid velocity, so seawater velocity on thermal sprayed aluminum corrosion. So without further ado, I would ask Kranti to present the talk on zinc electroplating. Over to you, Kranti.
Thank you very much, Elijah. Let me share my screen. I hope you are able to see my screen. Yes. So good morning, everybody. Today I will be talking on the alternatives to zinc electrolytes, which are based on my Marie Curie project, that is INHALE. So the outline is pretty simple. I'll try to introduce what is zinc coatings, and I'll take you to the story of how my objective was framed, and I'll present you some results which were done as a part of my Marie Curie project, and finally I'll conclude. So zinc coatings are most commonly identified for the corrosion protection of steel components, and because they exhibit good sacrificial property with electrochemical potential, because they have an electropotential less than iron, they act as a sacrificial layer. And also it has the advantages is that it can be plated with other metals like nickel, cobalt, iron to improve the corrosion resistance. And you can see that it can be applied with different methods, but electrodeposition is one among them. And you can see that the person behind the electrodeposition and electroplating was professor. And you can see an example of how an unplated coin versus the plated coin looks like. So that is how the plated components look like, and that is advantages of what you have with plated components. You can have a thin layer and which can really have which can accommodate the corrosion protection, and you can use it for multiple applications. But zinc is known for the corrosion protection of metallic components. As I said before, it can act like a sacrificial layer, but since many years, zinc plating is known. But it started with cyanide zinc, which involved any hazardous chemicals, harsh environments, and from then many developments happened since then, almost 50 years. So it all started with the cyanide, and today we are in the position of reaching an electrolyte which is free from ammonia, which is free from cyanide and all these things. But still, you have the problem of aqueous, dealing with aqueous systems. The biggest problem is the hydrogen evolution. In addition to plating, you will also have an hydrogen evolution, which decreases not only the efficiency but also disturbs the property. They influence the property of the coating. So, if you look at the recent developments, as a part of the next generation electrolytes, they have been targeting on non-aqueous based electrolytes that are known as ionic liquids and deep hydrotic solvents, which are formed, which either have a large cation and a small anion, or which either have a hydrogen bond acceptor and donor. So they mix two components, which will then form a mixtures, and which doesn't release hydrogen. But the main problem is that they are all halide based, which is chloride or fluoride or bromide or iodine, which release chlorine and bromine gas that are harmful. So as a way forward, looking at halide free non-aqueous systems, which doesn't contain chloride, bromide, fluoride, is something which it can be considered as a way forward. And that forms my objective. That was the objective of my project, INHALE, which focused on the low toxic electrolytes which are free from halides and also which can still perform better than the current conventional or the newly developed ionic liquids and deuteratic solvents. So today I'm going to take you an overview on the coatings that were developed using the innovative low toxic electrolytes. And also I will discuss the corrosion performance, the scale up, and also the cost economics. And to understand this, first what I've done is I have taken a conventional halide-free alkaline aqueous systems, a cyanide-free as well, and I've taken an organic solution containing glycol plus acetate and a popularly known ethylene, which is choline chloride plus ethylene glycol. It is a depuritic solvent formed by mixing choline chloride and ethylene glycol in different ratios. So industrially used plating cell is the hull cell, which is 267 ml. Since we are dealing with organic solutions which are expensive, so we thought to go with a miniature cell known as ternary hull cell, which mimics the industrial plating cell. So that is used to optimize the current densities and make a comparison between the amongst the three electrolytes. That was the first innovative thought what we have got, and we applied a cell current of 0.1 amperes, and we computed the current densities along the things. And I would like to show a small video on how the plating happens when you apply a current of 0.1. You can see that the bubbles go near to the surface, and that is how it has the plating. So sorry about that. We used anode as a zinc, the conventional zinc anode, and cathode as mild steel because the main objective is to protect steel components. And what we have done is we deposited at different temperatures and different cell currents. From there, we derived the current densities, and we chose the optimal current density from that and try to understand the nature of the deposits and its growth. So for that, we chose two timings. One is 15 minutes, another is 13 minutes, and we characterized by using the X-ray diffraction and the microscopic methods. And you can see on the right, you have three different solutions. One is the halide-free aqueous, which is transparent and aqueous based. The chloride-based depuritic solvent is bit turbid, whereas the organic solution is clear. And this is just an optical microscopic image on the right, which shows that there is a coverage of the deposition, whereas the left image, the top left shows the ternary hull cell panels, which shows a full coverage, and the right two square pieces show the different depositions at two different timings by applying a particular current density. So we all know that halide-free zinc has a hexagonal structure, which helps to get which is the main reason why you get a good corrosion protection. So you can see that with increase in time, you can see the orientation is changing with regards to the depuritic solvents and the halide organics. So that depends on the transportation of the species. That is why you see a different orientation of the plane. But still, you can see that you have an hexagonal that is formed, a oriented hexagonal planes which are formed. And also we try to perform the cathodic current efficiencies by using the Faraday's law and the gravimetric analysis. And you can see that these organic solutions dominate with increase in time. When you increase the time of deposition, they cross the choline chloride based depuritic solvents. And this shows that the acetate based organic solutions have a good functionality, and they can perform better than the much more developed depuritic solvents. And if you look, this is an X-ray diffraction comparing the three different electrolyte systems. So you can see that a comparable planes were achieved with us, and we have the organic solutions mimicking almost the halide-free alkaline solutions. That is what you get. And we try to make a corrosion performance data by doing an electrochemical study. And from the TEFL data, it shows that you have similar corrosion potential, and you can see that almost the halide-free solutions and the it is mimicking almost the comparable performance. It is showing a comparable performance when you talk about the amongst the three systems. So which shows that the acetate-based organic solutions were really performing better. So with this motivation, I try to develop different organic solutions. I thought organic solutions would really perform better because of that was the motivation why I have performed the initial study using the standard benchmarks, that is the alkaline aqueous as well as the chloride based deputatics. So I could figure out that you have an organic solution, a halide free organic solution can perform better. So, and you can see that on the left, when you compare the cathodic current efficiencies, you can see that the organic solutions they are really performing better than the halide free ionic liquids. And also these are some of we've attempted to get 4 different kind of systems. One is the actual zinc, another is zinc, nickel, and cobalt and iron. So these were the things which we are achieved, and you can see the right side images were representative SEM images. So once we identified and once we got the similar corrosion performance, having understood that the corrosion performance of the organic solutions is equivalent to the conventional systems, we attempted to go for the scale-up solutions, and that is where we tried first. Instead of going to 5 liters, we went with 1 liter, which you can see on the left, and we instead of having a flat part, we went it with a bent cathode, because you will have a different mix of geometries, and the current density will be varying through. When you apply a current, it keeps varying from the front and back. So we need to understand how best we could get the coverage. That was the main objective here. And we had a 2-phase scaling approach. The one is the 1 liter scale to understand how good the electrolyte is performing. And you can see the plating line which was set up as a part of this project. And you can see that we also could perform the 5 liters. Once we got the good results with 1 liter scale, I went on to scale up for a 5 liter scale, and I did for a kind of a throughput where I plated continuously for 1 hour, 4 hours, 2 hours, and 4 hours. And you can see the bottom images. I would like to show you a video which you can see the plating happening in the tank, a 5 liter tank, and you can see that how good it is plating, and you can see the coverage that is happening on the top face, on the bottom face, meaning that you have a kind of a good coverage, and the efficiency of the electrolyte is good, and it can cover all the surfaces for a given current density and temperature. And once we could demonstrate that, okay, we could get this at 5 liter scale, we went on to perform the cost economics. So I calculated the price makeup for the organic solutions versus the ionic liquids for different alloys. And a representative plot is shown here. So you can see the electrolytes versus, when you compare the electrolytes versus the price, you see that comparative to the ionic liquids and depuratic solvents, you are able to achieve a lower price, and also you could achieve the performance, and you could also understand the stability. They are really stable electrolytes, so which indicates that they are economically feasible, technically feasible, and it can be taken up further. It has a commercialization route, so it can go up to commercialization. So that was the significance and of these plots and the study what we have done. So I would like to summarize. So what we have done is to understand the choice of depositions. I tried to compare between the 3 different systems. 2 were conventionally known, 1 is the new, and then I figure out that you have the halide-free non-aqueous organic solutions perform better, and they could get the similar crystallographic directions. And also you can see that in terms of efficiencies, they could yield better good zip deposit, and also better cathodic current efficiency for a given current density, and which shows that it has a better capability, and it can function better in delivering the properties that are intended for the corrosion protection. So And most important thing is that we could get the 002 peaks, which suggests the good corrosion resistance. And also we could do the electroplating scaling. So the study highlighted the necessity of scaling up, which was a part of the project, and I could do it in 2 phases. One is the 1 liter scale, and once I'm successful with that, and then I could expand it to 5 liter scale. So which showed the potential route towards commercialization. So which I could demonstrate that it has the capability to achieve commercial scales. So in short, this is the snapshot of the work which I've done as a part of my Marie Curie. So I started with a 33 ml tenory hull cell to optimize the current densities. I could do a 2.5 centimeter by 2.5 centimeter specimen using an 80 ml solution. Then I transformed it to a 1 liter scale, where I used not a flat part, but a complex geometry like a bent cathode to understand its coverage, and I could still get that. And finally, I could set up a line and I could run a throughput there, and you could see this is what you can get a good coverage. So these are the snapshot of what I could also get I could also perform an economic feasibility study, an initial basic economical feasible study to understand the price variations, what and its impact, how would, whether we do 1 liter, 5 liter, is this price viable, and it is feasible. Yes, from this study, we could safely tell that yes, it is a viable process, and it can run for longer durations incomparable with the conventional systems. That is the key takeaway from this study. And I would like to thank my team. Prior to that, I would like to thank the director of MatIC for giving me this opportunity, because I never thought about being a Marie Curie fellow, but it was only a dream for me. But Shiladitya was the person behind this to identify the potential in me, and I would like to take this opportunity to thank him. Thank you, Shiladitya, and my team here who are there always supporting me, and they were supporting me in many ways, and I thank all my team members. And last but not least, I would like to thank the European Commission for believing in me and my potential, and giving this understanding my proposal, and finding. I really thank them for understanding the innovative aspects, and awarding this fellowship to me. With this, I would like to conclude my talk. Thank you very much.
Thank you, Kranti, for that interesting talk on your Inhale Marie Curie project. So if you have any questions, please feel free to put that in writing in the Q&A, and Kranti would try to answer either now or later on when we have the Q&A session. So I would like to go to the next part of the talk, where we are going to talk about offshore corrosion and offshore corrosion mitigation. So to kick us off, Adamantini, please, the floor is yours.
Thank you, Shiladitya. Hello, everyone. Sorry, I have a very bad internet connection, so I will stop my video, but I'm here. And let me share my screen. Just a moment, please. Sorry. Can you see my screen?
Yeah.
Okay, so hello everyone. Today I'm going to give the presentation with title Testing of Coatings for Offshore Applications. As Silvia mentioned, I'm Adamantini and I'm working as a research associate in MatIC. So the tests that are going to be presented were performed as part of my PhD with title Novel Coating Systems for Mitigating Corrosion of Offshore Wind Turbines. And as we all know, offshore environments are very challenging due to UV radiation, fluctuating temperatures, floating debris, and also seawater, which can cause and propagate corrosion. So on the bottom side, you can see some images for offshore metallic structures. Here I'm going to talk a little bit about an offshore wind turbine. As you can see, there are different zones. Starting from the bottom is the buried zone, the submerged zone, the tidal or splash zone, as it is known, and last is the atmospheric zone. On the right-hand side, you can see the corrosion rates that have been reported for these areas. My study focuses on the atmospheric zone of an offshore wind turbine. Traditionally, cathodic protection is applied on different zones in order to tackle corrosion. However, due to the lack of continuous electrolyte in the atmospheric zone, I mean, seawater is the electrolyte, another approach has been followed for corrosion protection of this system. In this slide, you can see the development of the multi-layer system that was followed. And starting from the bottom, we have the metallic substrate, the sacrificial zinc aluminum coating, an intermediate coat, a paint, and on top we have another paint which sealed the whole system and also gave the white coloration to the system. And here in this slide, it's the project problem and how we approach to its solution. On image A, you can see the system that I previously just described, and on images B and C, you can see some artificially inserted scratches. So on B, the scratch has propagated till the metallic substrate. On C, it's on the zinc aluminum coating. So zinc aluminum acts sacrificially. On the left-hand side, you can see the calcareous deposit formation that can protect the substrate in its case. Here is on the top image, you can see the equipment that was used for the deposition of the zinc aluminum coating. I'm not going to talk into depth for this because Adriana is going to give you a better idea later on her presentation. And you can see that two wires were used, zinc aluminum. So on the next slide, I have the composition of the substrate and the wire consumable. So here we're going to focus on the material, the aluminum that was used. The minimum was 14 to 16. And for the zinc, it was around 85%. In order to test the success, the good approach of our system, mechanically scratches were inserted with a tool that is presented on the left-hand side. And on the right-hand side, you can see the cross-section of the damaged area and also the top view of the sample. These samples were exposed in field test area in real marine environment. As you can see, with the yellow circle is the test area, and it was 80 meters far from the sea, and the whole system approached the atmospheric conditions of an offshore wind turbine. On image B, you can see the area that the experiments took place. They took place in Santander and in Spain, and more specifically in the area of El Bocal. On the image C, you can see the samples, how were they exposed. And on the right-hand side, you can see that there is a corroded metal. It was a bare steel that was there for our reference. So the exposure conditions in the real marine environment, the exposure took place for 3 months from May till end of July, and the seawater temperature was around 14 to 19 degrees Celsius. The air temperature had an average of 17 degrees Celsius, and the salinity was around 35 PSU. Here you can see the bare steel before and after exposure to real marine environment. On the top, you can see that there is a gray coloration inside the scratch, and on the bottom, as expected, there is the typical orange-brown color of corrosion. And here are the samples before and after exposure, but this time they have the zinc aluminium samples. So we can see that the colors appear to be almost similar from before and after. In order to have a better idea of what was happening in the scratched area, some SEM images were taken with the backscattered electrons detector, and as you can see, some random areas were selected. Here is the results from the ADX analysis, and in order to give you a better idea of what happened, on the spectrum 3, we had oxides formation, which was quite high, and also noteworthy was the aluminium and zinc depletion. The next set of experiments took place in salt spray chamber at TWI, and here there is an image of the operation panel and a schematic representation of the whole salt spray chamber. So you can see that there is a chamber heater, the samples, and a salt spray fog that can be constant or not depending on the conditions that are selected. On the left-hand side, you can see the samples from the interior of the salt spray chamber. I would like to mention that they were exposed at synthetic seawater with different elements to be present. The salinity was around 3.5%, and the exposure took place for 1,000 hours at the temperature of 35 degrees Celsius. After the exposure, the samples were removed from the interior of the salt spray chamber, and they were washed with DI water, dried in room temperature, and then their characterization followed. And here you can see an image from before and after exposure. As you can see, comparing these two images, after the B one has a lot of white colorization, which we further examined with the same way like the previous sample. So as you can see, there are different formation on the top of this image, and the EDX analysis showed these elements on the top of the scratch. And as you can see, again, for spectrum 3, it was quite noteworthy, the depletion of aluminium and zinc, and also the formation of oxides. In order to have a safer conclusion of why these differences happened in the real marine environment and in the salt spray chamber, we found some previously reported data that from May till July, when the exposure took place, the sun conditions are quite extreme. So this is a reason why possibly this difference was reported. To conclude, it was not only the extreme UV exposure, it was also the rainfalls in the test field area, which also affected the presence of forming products. Although the exposure was longer for the real marine environments, the continuous corrosive environment in the salt spray chamber dramatically played a crucial role in this in the formation of these products, because the conditions were more aggressive. So in order to have a safe conclusion about the performance of this duplex system, it is very important to have a combination and a comparative study of field and laboratory tests. And with this, I would like to thank you for your attention. If you would like to further contact me and have a chat about this, this is my email address. And I'm taking the opportunity to thank my sponsors for making my PhD research come true. Thank you very much. I will now stop sharing my screen.
Thank you for that interesting talk, Adamantini. For attendees who are interested in asking questions, please use the Q&A function within Zoom to ask the question, and state which speaker you'd like to ask the question to or address the question to. So now I'll pass on the mic to Adriana, who is going to again carry on in the same theme as mitigating offshore corrosion, but for a slightly different system. Adriana, over to you, please.
Okay, thank you so much. I hope that you can see my screen.
Yeah, thank you.
Okay, yeah, thank you so much for this introduction. So for today, I prepare this presentation. First of all, I'm going to give you a small introduction about the background and experience in MatIC dealing with these coatings for offshore environments. Then I will give you the methodology to evaluate them in offshore environments. Finally, I'm going to give you some results, some conclusions, and one of the challenges for evaluating these coatings. So in MatIC, we have developed several projects. One of them is related with the protection of wind offshore turbines using low-cost, damage tolerance, and sacrificial coatings as response of the ambitions and the goals and the targets established by the European Offshore Renewable Energy Strategy. So in that sense, we are talking about thermal spray coating, and they offer several advantages. They offer a sacrificial protection for offshore structures. The process offers high application rate, low thermal transfer to the base metal, is a cost-efficient deposition technique. So basically, it's a good alternative to replace the conventional protection based on paint and anodes in submerged zones. So here you can see in the figure schematically the process. The twin wire arc process consisting to force two wires electrically charged to establish an electric arc. So in that sense, the material in molten or semi-molten phase are accelerated onto the substrate by a gas stream system. So we obtain a thickness of the coating onto usually S355, which is a carbon steel, quite common in offshore applications. So here on the right, you can see the different materials that we can have as consumable. So especially aluminum alloys. In my presentation, I'm going to focus in the alloy 1050, which is ideal for immersed zones. So understanding the corrosion behavior of these coatings, involved several techniques. In MatIC, we have developed several techniques, and they complement each other to understand how they behave in just not in laboratory, also in field tests, as Adamantini mentioned before. So we have several techniques with electrochemical methods in order to understand the corrosion performance of these coatings. But here you can see on the top the picture of the nature of the coatings. They have high porosity, also high roughness. So the aluminum is quite active in seawater, but also as it offers a cathodic protection, we can get a deformation of calcareous deposits. So also the characterization of those products are quite important in order to understand the mechanisms of them. Field tests, but also quite interesting to see the damage tolerance of these coatings. So here we can see a coupon with an intentional defect after some time of exposure. At the end, we can see the formation of this white, could be aluminum corrosion products or even calcareous deposits when the electrolyte reach the substrate. Also, it's clear that the defect of the exposed steel is covered by calcareous deposits without any signs of loss of corrosion. So in that sense, we have reported really low corrosion rate under stagnant conditions. Another important approach that we follow in MatIC is the real-time monitoring of this coating, as Shiladitya explained before, in order to see in real time what is happening and how we can correlate the surface activity with the electrical signal using different techniques. Finally, we have some progress in numerical simulation in order to establish the long-term performance of these coatings. So as you can see, it's complex. The coating, involves many things, but today I'm going to focus on the effect of flowing conditions on the performance of thermally spray aluminum coatings in synthetic seawater. So first of all, what we note basically is that these coatings have been reported to provide cathodic protection to the steel and have low self-corrosion. Laboratory tests and also field tests demonstrate that they perform very well. After some time of exposure, we found aluminum corrosion products and calcareous deposits, and they precipitate the surface, but also inside of the pores of the coating, which is beneficial because it reduces the self-corrosion of the coating. However, in real life, these ocean currents can remove these protective layers. So unfortunately, it's not clear how they affect this removal of these protective layers. There is a little information in the literature on how the flow affects. These coatings are complex because the porosity and the trend and roughness, and it's a bit challenging to study and give a quantitative value of the rate of degradation. For instance, there are some studies that report the corrosion rate based on mass loss for this coating. However, it might not be practical because the pores are filled with corrosion products. In addition, the chemical procedure to clean the surface can result in an excessive removal of the metal. So for the reason there is a high corrosion rate on these studies, but the procedure cannot be appropriate. So this study looks to evaluate basically the effect on flow velocity on TSA corrosion rate, its impact on the aluminum activation during the first days of immersion in synthetic seawater. For that, we follow this methodology. So here we can condense basically the procedure. We machine cylindrical inserts from a S355 rod. And we obtain the coating using the parameters that you can see on the top with this in this table. So this is it's a cylindrical insert with 12 millimeters of outer diameter. So in that sense, the surface under study will be 3 centimeters squared. So, and actually you can see the coating here. There will be the coupons with a thickness of around 300 micrometers, high roughness around 43 micrometers. So on the bottom, we can see the element composition of the material of the substrate and also the coating. So in this case, we are going to evaluate this coating for immersed zone, and we have 99% of aluminum. So basically, to evaluate this coating, we use a rotating cylinder electrode. Here, using a 3-cell electrode. Here we have the working electrode that are our coupons that we described before, using silver chloride as a reference electrode and 900 milliliters of synthetic seawater. So this is a commercial rotating cylinder electrode. The electric unit allowed to us to set the velocity at 50 and 600 RPM. If we convert this velocity in linear velocity, so we are dealing with 3 centimeters square and 38 centimeters per second, sorry, and a room temperature. So after 10 days of exposure to these coatings, we collect information and analyze them. So basically, we monitoring the open circuit potential and the linear polarization resistance. And the scans were obtained at 10 millivolts per minute, polarizing at plus minus 10 millivolts regarding the corrosion potential every 6 hours per 10 days. And the corrosion rate was calculated follow this equation, and we use naturally the current density that we obtain from LPR. So as result, this is the aspect of the coupons before and after exposure. So the black arrows indicates the direction of the flow. So basically we can observe that the coupons doesn't have any signs of rust or damage of corrosion of the substrate. However, we can see that these white corrosion products appears on the surface and they decrease when we have high velocities. So basically, under flow conditions, the hydroxide ions can evacuate the interface rapidly, and the interfacial pH doesn't increase enough to promote the precipitation of these calcareous deposits, or even if there is any precipitation of them, they can be removed by the flow. So naturally, it will have an impact on the kinetics and degradation of these coatings. So here we can see the records of the open circuit potential and the LPR, the scans of LPR over the time, and in the 3 different cases. So basically, at the beginning of the immersion, we have a drop of the potential. It happens because the air oxide layer formed on the aluminum, it's activated, and it's clear that in all cases, the system reached the protective potential for carbon steel. In stagnant conditions, we observe similar things that we have reported before, low disactivation and kind of stabilization of the potential. However, and at 50 and 600 RPM, so we can see the fluctuation of the potential, which is not, it's unusual for stagnant conditions. So we can attribute this fluctuation to the formation and elimination of these corrosion products of protective layers by the flow. Actually, in the bottom of the tank, we observe these compounds at 50 and 600 RPM, which means that they dislodge from the surface during the experiment. So finally, with this information, we calculate the corrosion rate. So what we can see that all systems at the beginning, they have a high corrosion rate because the activation of aluminum. However, it's clear that at 50 and 600 RPM, we got a higher corrosion rate. So the protection mechanisms offered by TSA, it's in seawater involves forming corrosion products, passivation tendency of aluminum, and precipitation of calcareous deposit. I will say that the main advantage of these coatings in marine environments is due to the synergy of all these things happening at the same time. However, if these protective layers are removed, so then the aluminum is reactivated and then the corrosion process might accelerate. So as conclusions, it's clearly that hydrodynamic conditions strongly influence the corrosion rate of the TSA and also the precipitation of calcareous products and corrosion products, at least during the 10 days of immersion. Nevertheless, the ability of TSA to provide cathodic protection to steel is quite evident. We report in these experiments low corrosion rates under stagnant conditions, around 0.012 millimeters per year. But of course, they are higher with 50 and 600 RPM. However, if the corrosion rate will decrease over the time, if these layers are more stable over the time, is not clear with these short experiments. And of course, more research is required. So yeah, basically as challenge and future work, it's important to identify also the corrosion products and deep examination of the cross-section before and after exposure in order to consolidate in a better way the corrosion mechanism, because we have mass transfer in the system. But it give us a good idea and about the corrosion rate, especially in the first days of immersion. And finally, I would like to thank you for your attention, and please don't hesitate in contact me if you have questions regarding this topic.
Thank you, Adriana, for that presentation. Very interesting to see some of the techniques that you have been using. And for the audience, if you have any questions related to this or any other talk this morning, please use the Q&A function within Zoom, and please let us know whom do you ask that question, or address the person you'd like to ask the question. And then when we go into the Q&A session, we'll address those. Thank you very much once again, Adriana. And the next speaker for today is Naomi. And she's here with us now. She's the principal scientist at OST. And she's also the chair of Young EFC. And given I've been involved with EFC for a number of years, it's great to see Naomi today. So over to you, Naomi. Naomi is going to talk a little bit about Young EFC and how we are trying to build up a network of people interested in corrosion within Europe and beyond. So over to you, Naomi.
Yes, let me just share my screen. I think, no, it's good, right? Yes, you should be able to see my screen, right?
Yes, Naomi, yes. Okay,
perfect. So as Paul says, thank you for the invitation. My name is Naomi. I'm here because I'm the chair of the Young EFC. I took the chair in 2022. Here you can actually, I put QR code in my whole presentation, so you can actually screen through our website, even if you review it, so you can have more information. So what is the Young EFC? So we're part of the European Federation of Corrosion. If you're not familiar with it, if you're a member of your national society, you're automatically a member of the European Federation of Corrosion. Because you're most of you in the UK, if I'm not mistaken, it will be ICOR for you. But for the Young EFC, it's actually free of charge. You just have to fill up a form, just say like, hey, I would like to be a member of the Young EFC community, and then you're a member. What we try to do is actually to support early career professionals in the field of corrosion and protection of material, and we try to organize events, so not only in science or a topical event, but also more about soft skills, networking event, because for us it's very important that we developed this networking and that we foster collaboration, or if you have a question and so on and so forth, so that you have actually a platform where you can exchange. So that's basically our main goal. So what do we do? First, who are we? So we are different. We come from different background. We also in different European country. We also basically come from all over the world. I'm actually did all my career in academia, but we have now half of the board that come from industry. So we're trying to push as well much more event towards what is good for young professional working in corrosion industry or material protection. So if you have idea, if you feel that we're missing something, so please just contact us. We are really willing to start new thing as well, because we're here to help the community to grow. That's basically our main task. As for personal development, what do? We offer advanced paper writing webinar in partnership with Elsevier and Corrosion Science. We have science communication event. We will have some grant writing that will be this fall, and we collaborate with the Correct program, which is located in Canada, through a mentorship program. So the next call is in September 24. If you want to be a mentee, if you want to be a mentor, please have a look. It's very nice as well to meet people and to basically, if you're stuck or if you want other career opportunity or see basically, yes, so have a look at the mentorship program. We also organize virtual workshop. We had one last week. Where we had first a lecture on corrosion, and then we had actually break room on leadership, career opportunities in industry, how to write a CV. All of these workshops are available online, so have a look at the Correct website. And basically you can receive most of our webinar. We try to record and they're available on the Young EFC YouTube channel as well. So if you miss one event, have a look there. You may be able to listen to it again. We, of course, as well promote award and grant. You do not have to be in academia. If you work in industry, you're eligible as well for this event. And the next call will be in December 24. I must highlight that is really not competitive. I think this year there was no one applying for the Young Scientist Grant. So this is an opportunity if you want to do a research day or a visit to a partner of the EFC, apply. Really, like it's a unique opportunity. And as I said, you have high chance to get it if you apply. You just have to apply. Of course, if you want, or if you're unsure, if you fit, or if you, as me, you don't think that you will be eligible, have a look. We have basically as well, we have interview about who are the winners. So you can see that they're actually normal people. They were just normal people applying to it. So have a look there. And we promote as well women in corrosion. So this year we had a wonderful career webinar with Jennifer Locke. Jennifer is a professor at Ohio State University, but interestingly, she started her career journey in industry And she basically discussed her career path, but as well, she gives wonderful advices on early career professionals. So again, here you can listen to it on YouTube. We also we supported the organization of the Women in Science Week. And there, if you plan on submitting a paper on coating, we have a special edition for women working in corrosion, where you can actually, there will be a special edition in the journal Coating, so have a look there as well. And of course, like we are all here today for Corrosion Awareness Day, so there we promote activities throughout the world. We had a topical event yesterday about corrosion engineering versus corrosion management. There as well, if you missed it, you can listen to it on YouTube. It still hasn't been posted, but I will do it tonight. So from tomorrow on, it's available. And we were part of the VCO, EMPP, and EFC social media campaign. Just look at it on LinkedIn if you're there. It's amazing what people posted throughout the world about corrosion and corrosion awareness. So if you want to see a wonderful picture of basically what is happening around you, I will highly recommend it you that you have a look at this. One main event, or basically the only event where we all see each other during the year, it's at Eurocore. If you go there, come to our annual meeting. It will be on Monday evening. And this year, the get-together event is actually combined with a career fair. So we actually try to mix up like people seeking a new career opportunity with industry and academia that are looking for new talent. So that will be a unique opportunity for you to basically informally meet maybe a future employer. We have a young EFC plenary lecture which will be given on Tuesday morning. Every year we run a 3-minute plenary lecture competition. So the winner this year was Emilio Martinez Paniena. You can apply as well next year. It will be run again. So have a look if you want to give a plenary lecture. And this year, it started last year, but this year we have as well have 2 Best Oral Presentation Awards that will be given. But we ask that we do a pre-selection because otherwise it's too much to evaluate. So if you want to participate, you just have to send a 3-minute video by July 28th. So here as well, the QR code, have a look. If you want to participate, the eligibility criteria are there. Our next event, we have an online webinar coming up on May 21st on corrosion performance of additively manufactured metal. There as well, look at our website to know how to register. We will have a career webinar with Jolanta Erdberg in June. And there's still you can still apply for a registration fee waiver. So that is organized by VP10, the microbial corrosion. Have a look there as well. If you work in the field of microbial corrosion, that's a unique opportunity for you. And of course, there's the EFC Summer School that will basically be held in Paris just before Eurocore. If you work in corrosion in green energy and technology, or if you want to learn more, that's as well a good opportunity. You will have a visit of different companies in synchrotron, and there will be amazing speaker. If you do not do it yet, I will invite you to follow us on LinkedIn. There you can actually see what is happening in the EFC and the Young EFC. And you can join as well the EFC Hub. So the idea is that is kind of a research gate, but for corrosionists. So if you work in corrosion and material protection, you can find the community there. And as I said before, if you want to become a Young EFC member, you just have to go on the QR code there, and you get an email every now and then about where the award and the career opportunities, the event. But if you want to get more involved in the Young EFC, basically just drop us an email or just contact us at an event or something like this. So that's about what we do. If you have any question, I'm happy to answer them anytime.
Thank you very much for the interesting presentation, Naomi, talking about Young EFC. And I remember when Young EFC was founded. I've been part of EFC, going back 12 years now. So yeah, great to see that the initiative is growing and more people are interested in getting interested in STEM field, and we have a huge scarcity of skilled professionals in the corrosion field. So it's good to see that Young EFC is trying to plug some of the gaps that we have.
Yes.
Okay, I think it's time for the Q&A part of the session. So if you have any questions, please use the Q&A button or the function in Zoom and let us know whom that question is addressed to. So we had a question from Nick Clark for Adriana, asking a bit more about the calcareous deposits on TSA. So Adriana, a quick question from my side on that. So we know that you explained that you do tend to see calcareous deposits on the cathodic surfaces or surfaces that are predominantly cathodic. So would you only see calcareous deposits on the steel surface if that is exposed? Because we know in TSA steel combination, the steel would act as a cathode. Or would you also see cathodic deposits or calcareous deposits rather on top of thermally spread aluminium?
Yes, it has found some calcareous deposits on the top. It is mainly because these coatings they have a high porosity, and sometimes the electrolyte can go through these pores and reach the substrate. So it's possible to find these compounds. I'm not saying that is the main product because it's aluminum corrosion products, the most likely. But yeah, we can find also over the time, actually. Probably in my experiment, they are short time, but with more time of exposure, probably we can find these compounds.
And would you say that you can see these compounds only if you have defects within the TSA, or could that actually form on aluminium?
Well, we observed these calcareous deposits mainly in the cathodic areas when we have exposed steel, but also in the pores of the coating they can be. But to be honest, I have observed these calcareous deposits only on the cathodic areas. So yeah, it's not possible to identify calcareous deposits on aluminium itself, in this layer. So
because I was thinking, even if you take just aluminium and there's no steel, let's say a monolithic block of aluminium, you'd still have anodic and cathodic regions.
Yeah,
right?
True.
So if there are localized cathodic regions, it's going to likely to be stochastic in nature, but would you still be able to see that there might be, especially in cathodic regions, you might form calcareous deposits if you're using seawater in those cases?
Yeah, if we've had these cathodic areas, because also we have the cathodic reactions, and also the degradation of aluminium also reduces the pH. So it could be a factor which can promote the formation of these calcareous deposits.
But if the aluminium corrosion is locally reducing the pH, then it's probably not conducive to calcareous deposit formation, because we know that the pH needs to go
increase.
Locally needs to increase to actually have magnesium and magnesium hydroxide and calcium carbonate forming, right? So it could be that if you have conditions where localized corrosion of aluminium is reducing the pH locally, then the calcareous deposit formation may not be actually preferred in those low pH conditions.
Yeah.
And there was something else also Nick mentioned, which seems quite interesting, is when we do our test, or when you have done test and Adamantina as well, you have used synthetic seawater. So tell us a little bit about why you have used synthetic seawater, because quite a lot of people think that, okay, we can use sodium chloride as simulated seawater, and why you have used something different from sodium chloride.
Okay, so yeah, we use synthetic seawater because it has the main compounds, generally that natural seawater. So it has the salts responsible for the formation of these calcareous deposits. And probably from sodium chloride is not relevant because we don't have these compounds. So we have a structure under cathodic protection. So we promote this increasing of pH, of local pH, and also we promote the formation of these calcareous deposits, which are beneficial and reduce the cathodic area. So for sodium chloride, I will say that if we want to evaluate the structures in an offshore environment, it's not under cathodic protection. Naturally, it's not. It could be a bit different. So yeah, that's the reason because we are using synthetic seawater instead of sodium chloride.
Thank you, Adriana. I think this is one of the things that preparing synthetic seawater is a bit more complex than just having sodium chloride. So I guess a lot of times, it might be easier to just use sodium chloride. But what you're saying is one needs to bear in mind that the behavior in seawater could be different from what you see in sodium chloride.
Yes.
Thanks very much, Adriana. We have
Thank
got
you.
another question, this time for Kranti. A question from Freddie. The question says, was corrosion behavior of the new zinc electrodepositor coating from halide free also compared, or how did they compare to mature zinc aluminum electrodepositor coating? And what was the effect of coating density on corrosion behavior?
Yeah, I think we have not studied on the zinc aluminum electrodeposited coatings, but increasing the density of coating may not have an impact on the corrosion behavior. The reason being because once you increase the thickness of the coating for the electroplating systems, they don't adhere well to the surface. That is where you lose the property of the coating. Initially, it might act like you have a good corrosion mitigation property, but as it proceeds with time, you may not see the actual the corrosion seems to be deteriorating. The basic you'll see a loss of coating. So that is where the problem happens. That is where you need to find a balance between the thickness of the coating and the corrosion performance. That is what we need to do about it. But zinc aluminum coatings is something the challenge in achieving the aluminum electrodeposition is one of the key research things which people are really trying to find out. So I think that can be the future study because direct deposition of aluminum from the systems like zinc, it's a bit difficult at the current situation. So we need to find a mechanism to develop an alloy and compare with zinc aluminum. But if I have not made a direct comparison between the electroplated zinc and other zinc aluminum coatings. So
Kranti, following on for that, so I think we know that in ecosystems you're going to hit the hydrogen overpotential before you actually plate aluminium, so it's not going to be possible.
yes.
But because you have worked on non-aqueous system, do you see a strategy for developing such coatings?
Yes, we can definitely see that strategies, provided the solution what we are trying to choose or what we choose should have a good electrochemical potential window. If you have a good electrochemical potential window, then this kind of compositions is achievable, especially when you have a huge potential difference between the zinc and aluminum.
Thank you, Kranti. There was a question from Nick where he was wondering whether presence of biofilms or biofouling would have an impact on coating. And I know, Adamantini, you did some work on offshore trials and you presented some of the results. So from your experience with field tests, and I know Adriana also did a bit of work, from your experience with the field test, Adamantini, do you have any thoughts on whether you get biofilms and other compounds of organic origin when you test these coating systems in offshore environments?
Thank you for the question. I'm not sure because I was focusing on the atmospheric area. So I haven't seen something for these films. Yes.
Yeah, I
so-
think because you're looking at atmospheric zone and your coatings were a few tens of meters away from actual seawater. So I think it's probably less likely that you would have seen some marine growth. Maybe let me ask the question to Adriana. Adriana, from your experience, because I know you did actual immersion in natural seawater in some of your work. So did you see marine growth, an extensive marine growth, and what was your experience?
Well, not really. And I mean, the samples still are under evaluation of this corrosion and formation products. But the difference that I observed between synthetic seawater and natural seawater was that probably the density of these calcareous deposits are less visible, just for visual inspection, are less than synthetic seawater. But yeah, sorry, the samples are under evaluation and see if we can get some of this formation, but I'm just talking about the visual inspection that we got in my experiments.
Thank you, Adriana. There's a general question from Ali Fahim, and he's asking, while the corrosion basically rely on the speed of exposing to the speed of exposure of electrolyte to the substrate, but could you achieve a very thin layer, say, let's say nano sized layer, that will delay this exposure by way of longer time? I'm not sure I follow, but what is the area of production in terms of the scale? So I guess this question is probably for Adriana. So Adriana, when we talk about defects and you're beginning to see a layer form, so could you quantify the thickness of some of these protective films that you're seeing and how they are growing as a function of time?
Yes, actually with the cross section over the time, I'm talking after 3 months of exposure, clearly we can see from the cross section that this calcareous deposit actually is a bilayer. And on the surface, we have magnesium compounds. And then we got calcium compounds. So it's basically a bilayer. A couple of micrometers. So it's possible by SEM to see the thickness of these protective layers. So yeah, I'm saying a few micrometers, maybe. That's the scale that we got. But okay, this is also dependence of over the time. So if more time of exposure, we got more thicker of this protective layer. Just the first few days, we got this film, but the thickness is less.
And also, as you mentioned, it depends on the velocity, fluid velocity
Yes.
as well.
Yeah. The
so you might
formation
form a film and then goes to a critical thickness, and it might fall off, isn't it? Because of the velocity.
Unfortunately, this time was too short to explain also some experiments that we can do with defect, because today I just explained TSA, but when we have defect, it means exposed steel, more cathodic areas. So we already know that the formation of these these calcareous deposits are strongly influenced by the hydrodynamic conditions. So we can see different rate of formation. So yes, it has a strong influence. I'm talking about this thick of protective layers when we are dealing with stagnant conditions. But still we need to deal when we have a movement, we have flowing conditions. So probably it's different. It's quite different, yes.
Thank you, Adriana. So I think we had a couple of talks where we are talking about networks. So Irmak talked about the power of collaboration and how the innovation network is helping community develop research ideas and take them through the whole cycle of getting funding, and we have benefited from that collaboration. I'm also part of the EFC community, where we work quite closely, academia, industry, try to understand and solve corrosion problems. So here's a question for both Naomi and Irmak. How do you see that these two seemingly independent networks, could we bring them together to collaborate and help develop a bigger community where we can work together and try and solve challenging problems associated with corrosion? Perhaps I'll start with Irmak and then go to Naomi.
Sure. Thank you very much, Shala. I mean, the answer is obviously, absolutely. What we are trying to build is not, obviously, we are trying to build our network with regards to developing these innovation centers, assisting SMEs, etc. But the real meaning behind it is really reaching out to a wider audience. So any opportunity to get together with different associations, different organizations would be beneficial for the network itself. So that would be a great opportunity. And the way we can do it is obviously looking for some opportunities with regards to any challenges, any upcoming calls, so that we can bring together these different actors that we have in our network. So that would be a great way to go. But I don't know if Naomi is going to say something else.
I agree. I think as well, at the moment, there are many opportunities to collaborate or to network, and I think people are willing to as well. As I said, like for instance, the UFC is starting to do a lot of summer school. There's this grant award where you can actually visit a group if you want to collaborate. So that's the more concrete. How do you do it? Because most of the time, let's face it, is a problem of funding. You can have a great idea, but if you do not have the funding to do it, that is basically always a bit of an issue. How to meet the people? I will say that it's by organizing. Like today, I was very happy to be invited to give the talk, because if you know that there is this type of network, and as I said, we now collaborated on this social action with EMPP. We're trying to do more things with them as well. We are trying to do things with the ACA, so the Australian Asian Corrosion Association. And as I said, we collaborate now as well tightly with the Canadian Core Mentor Program. So that is basically actor or talent that you may not meet at conference like Eurocore, because it's basically different continent. It might be too expensive, but there you can as well get other perspective. You can get new collaboration, you can have more pools. So I will say that by collaborating with or by collaboration between different entities, that is where we get the talent together. And that is what we're trying to do with the EFC Hub. So to create this platform where basically people can exchange or say, oh, I have this question, is there an expert there that can help me moving forward? It's still like ongoing, which means that it's not there yet where we want it to be, but it's one tool that we are pushing really because we see a need to have that.
Yeah. I think it's very similar to the TWI or platform that we have, where we are trying to bring different actors, like we said, organizations internal and externally. So yeah, and like you said, just one final thing, Sheila. I think what we are doing is a bit crucial here, because we are trying to build these collaborations around funding opportunities so that it really drives the opportunities of the collaborations. Otherwise, it's sometimes difficult to get different partners involved in it, you know, try to design something around it. But what we try to do is really match these with any opportunities that we can have. So it would be a good baseline to develop these relationships. So hopefully, yes, we would love to have more relations. So yeah, thank you very much.
Thank you both. So that brings us to the last bit, which is closing statement from me. So I would like to thank all of the speakers for excellent presentation, talking us through with what they're doing, creating networks, trying to solve challenging problems to avoid situations like these, where you have got, I think everybody here is trying to solve problems, and for the corrosion community, we want to try and avoid reaching that kind of situation. And for those who participated, please feel free to send us your comments and questions. And thank you very much for attending. And we had the last one in 2022. So thank you very much for attending this year's Corrosion Awareness Day talk. And we'll hope to see you again in the next talk, hopefully next year. And have a good day wherever you are. Thank you very much.